Hello, everybody. Welcome back to another lecture and video on data structures and algorithms. Today, we are going to introduce our first data structures, arrays. Specifically, we are going to talk about static fixed size arrays. As part of the lecture, we will introduce arrays as a data structure, what they are, how they work, what properties do they have. We are going to focus quite a bit on discussing time complexity, as well as what are the pros and cons of using arrays as data structures. And then we're going to see how to implement arrays specifically in C++, and we will talk at the high level how to implement them in Python. So let's get started with the first question. What are arrays? Arrays are a data structure. We defined what data structures were in the very first lecture, ways for storing, organizing, accessing data, and arrays is one of such ways. Arrays are fixed in size. That means that they are not changeable in terms of their size. Once we create an array of a certain size, we can change the existing size of the array. They are created in such a way so that they store elements one after another in contiguous memory locations, right? So if I have elements which can be integers or strings or any other data type, they come one after the other and they are stored in consecutive contiguous memory locations. So the main properties of arrays are one, their fixed size. We define the size of the array when we create it, and we cannot change it later. If we need to change it, we have to build a brand new array from scratch with a bigger size. So we say arrays are fixed in size. In addition to that, arrays are very powerful because they allow us to index into the elements of the array the sequence of elements that we have, the elements that are coming one after the other, have a specific index, which generally starts at 0. So when I need to access an element in the array, I can access it by the index. I'm going to show you in a slide how that works and what the mechanism behind that is. As we said, it is contiguous memory. Elements are stored in chunks of memory that are one after the other connected together. That allows for that fast indexing access. And then finally, generally, we store elements of the same type. So they tend to be homogeneous. For example, I can only store integers or I can only store booleans, but that depends a lot on the programming language. Overall, arrays are called the same throughout multiple programming languages. They're called arrays in C++, they're called arrays in Python, they're called arrays in Java. The majority of these properties, such as fixed size, index elements, and contiguous memory, are shared across multiple programming languages, but whether the elements are homogeneous or not in the array will depend on the language. For example, in Python, you can put in the same array different types of elements. In Java, you cannot. And we're going to see some of those properties as well as we work today with C++. If I were to visualize how an array looks like, it would be something like this. So here is my array of currently 10 indices starting from 0, right? So we start at the first index 0 in computer science. We generally start counting in 0, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count that in total, there is 10 slots. We call those boxes slots or buckets, and that's where the elements go. Now, each of the elements, as I said, is related to a specific index. For example, if I'm storing the value 45 at index 5, I can access it, I can modify it by directly going at index 5, right? So fixed size, 10 slots, 10 buckets, the length is 10. They're indexed. Each of the elements is one after the other. They have an index starting at 0, and this is a contiguous memory location. Now, why do we say that arrays allow for fast indexing, and how does it even allow for indexing to happen? Let's look at how arrays would look like in memory, right? Let's assume that this is my array, again, 10 slots, the size is not changeable, and I'm starting index 0 at address 0000. Okay, so this is going to be my base address. Each of the slots here will store an element, and let's say that it has a specific size in terms of bytes. Let's say it's 4 bytes, right? So if I start at 00, this is going to be at 0004. This is going to be at 0008. This is going to be at 00012. This is going to be at 0016, and this is going to be at 0020. Right? So by knowing the size of each individual slot, right? In this case, let's say it's 4 bytes for simplicity, but it can be 8 depending on the operating system or the implementation. or the data that we're storing into the array, I can very quickly calculate the particular starting address of any of the slots or the indices, right? So if I know the start address and I have the index, I can calculate with a very easy formula where I'm starting at, right? 0, 0, 0, 0 plus my index multiplied by what size I have. In this case, it's 4 bytes, right? And that is going to give me the value 0020, and that's how I can have that fast access. So that's why calculations and accessing and modifying values by indexing an array is so fast. Uh, um, and that's why we also store them in contiguous memory locations, because we know that after this element, this other one comes, and after this element, this other one comes. This is very similar to how you may have seen arrays are stored in the Intro to C class, right? And you can review that lecture to get a little bit more idea of how arrays work. But in a nutshell, again, arrays, fixed size, sequential element, contiguous memory locations. We know the starting address, right? And based on the starting address, I can calculate the address of every further slot by knowing at which index I'm at and how big is each individual slot, right? That allows for that very fast access. And while we're talking about complexity, let's go and discuss each of the operations that I will be able to do in an array one by one, okay? So this is a big table, but we're going to take it one step at a time. The first operation that we're generally interested in doing with arrays is accessing an element, right? So going at index 5 and seeing what is stored there, or going at index 3 and seeing what is stored there, or updating the element, going at index 3 and changing the value stored there, going at index 5 and changing what the element stored there is. The best case and worst case scenario for both accessing and updating elements is all one. Again, why? Because the array is indexed, right? The array has contiguous memory locations, so I can very quickly apply that formula internally, right? We're not doing that explicitly, it's happening implicitly with our access operations or update operations, and I can say, here's the start, here's the index I want to be, the address of this index is this one, right? And then I go straight there and I access or update the element, right? So that's why arrays tend to be a very popular data structure. Access update is super, super fast, constant time, both in the best case and worst case. In terms of inserting the elements, if there is still space in the array, right, because we said that the array is fixed in size, right? So if there's still space, if we're inserting at the end of the array, that's all one, right? Because my array is, right, as follows. So I have elements here, I have elements here. So if I'm going to insert, I'm inserting at the end, that's all one, right? I know where my last element actually is located. I just go there, put my element, my index access is very quick. However, if I'm trying to insert an element at the front, right? So if I'm trying to insert over here and the front is taken, I need to shift each of these elements over, right? So this one has to shift by one, this one has to shift by one, this one has to shift by one. So I can create a little hole to insert my new element at the front. Because I am shifting elements one after the other, complexity in that case is going to be of n. If I have n elements in my array, I'm shifting n elements to make space for the new one. So insertion is interesting, right? Depending on where we insert, if we're inserting at the end, the complexity is all 1. If we're inserting at the front, complexity is all of n due to shifting. Now, in the scenario that we need to insert, if there's no space for an array, this is not possible. We're going to see in a future lecture dynamic arrays that allow us to expand dynamically as more elements are inserted, but for fixed size arrays, that's not possible, right? If I declared an array of size 10, if I claim this chunk of memory, I cannot expand this specific chunk, right? 10 is all I get, I cannot resize. If I'm trying to delete an element, deleting an element at the end, again, is going to be all of 1. Same reasoning as we had with insertion of the element in the array, right? I know where the end element currently is, right? So let's say this is my array, and then I have elements here, 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 and here. If I delete this element, this one over here, that's quick. I just go there to that index, I remove it, all 1. But if I'm deleting an element at the front, right, I will have to shift all these elements over. So that is going to require an all of n complexity, right? So removing an element at the front, shifting everything over that requires of n complexity. So as you notice, both insertion and deletion have similar best case and worst case runtimes. Best case if we're doing operations at the end of the array, worst case is if we're doing operations at the front. And then finally, searching. We're going to talk a little bit more about searching in a couple of lectures and introduce different algorithms. But if we're searching an element, just like we saw with the book, a room full of books example, if we find the element at the very beginning of the list, the runtime is going to be O of 1. However, if we go element by element, the worst case scenario is O of n. This kind of algorithm is called linear search. We'll discuss it in more detail when we jump to the search algorithms lecture. But if we applied other search algorithms like binary search, we can get a little bit better of a runtime log of n. And again, we'll talk in more detail why binary search runs in log of n. But the best case, we cannot do better than O of 1. So both with linear and binary search, we cannot do better than O of 1. I'm sorry. So both with linear and binary search, we run in O of 1 best case scenario. In the worst case scenario, we are running either in n or in log n. So in a nutshell, these are the different operations when we are working with arrays. These are the time complexities. What I would encourage you to do is to take this table and cover each of the best case and worst case scenarios and reason and logic through them, and then compare your answer with the reasoning that we have on the side here in the slide. This is very good practice for you to get comfortable with how time complexities work. If we're talking about space complexity, when it comes to fixed size arrays, they take contiguous chunks of memory, right? That can be both a positive and a negative. The positive portion is that we can quickly access the elements because they're contiguous. We can do the calculation when they're located at. But the negative part is that if we're storing multiple elements, a million, a billion, a trillion, we need contiguous memory for that, right? And that can be a downside because that's a lot of memory. So time complexity is what we have here. Space complexity depends a lot on how we're using the array in terms of size. So a summary here, pros and cons. Pro for arrays, very fast memory access. I can very quickly update elements, modify elements. Any kind of applications when you're trying to frequently access values, arrays are really good at that. However, the negative side is that it's not efficient for inserting or deleting at the front, right? We said we need to, if we are trying to insert, we need to shift to create space. If we're trying to delete, we need to shift to fill up the space. So they are not really good when you're doing insertions or deletions at the front. They're not very good when it comes to memory for large sets of data, right? So if we're talking a million, a billion, a trillion, you need contiguous chunks of memory, and that's a lot of memory. And they don't resize. They're not dynamic. We're going to talk about dynamic arrays in the next lecture, right? So these are the overall pros and cons of arrays. One thing that I want to mention in general about data structures is that they are not one size fits all, right? Depending on the scenario that you need, one data structure may be better than another one. What do I mean by that? If you have a small set of data and you need to frequently access your data, then arrays are perfect, right? Because a small set of data is not taking a lot of memory and you have frequent access, right? But if it's the kind of scenario that you have a lot of data and the data for some reason is being inserted at the front, arrays are not good for you, right? So there's no one size fits all data structure. We choose a data structure based on the scenario that we have and the pros and cons of the data structure. As we move through the lectures in the semester, we will see how arrays can be used as a basis for implementing other data structures based on the pros that they have. So in a nutshell, arrays, a data structure of fixed size. It allows indexing. It allows sequential storing of elements. It requires contiguous memory access, but operations tend to be very fast when it's in terms of access, update, modify. How do we implement arrays, right? Every programming language is going to implement them slightly differently. In some languages, you don't have direct access to the memory, so we may not be able to work with the array directly. In other languages, such as C and C++, you have more direct access, more power with the memory, so you can see a little bit more how arrays work. So arrays are implemented a little bit differently depending on the programming languages you work with. So let's start and see how they're working in C++. There exist two types of ways that we see arrays in C++, two ways that we implement them. The first one is called static arrays or fixed size arrays. These are very, very similar to arrays that you see in the C programming language, right? They are much more limited in their functionality. They have some quirks. We're going to see examples of that today, and they don't tend to be super safe, but they are very similar to the C-style arrays. To introduce a lot of safety, functionality, flexibility, C++ has the standard library. And in their standard library, they have an std array type of array implementation, which is fixed in size, but it's type safe and has a lot of functionality opportunities that will allow, right? So we're going to see both of them. STL is something that you will come across quite a bit in C++. It's a collection of pre-built functions and classes and functionalities that provides to you common data structures. So if you needed to use a data structure in C++, you could use something from STL. In this course, we're going to be implementing a lot of data structures from scratch, right, to see how they're working internally, right? But STL simplifies quite a bit programming. On the other hand, fixed size arrays, right, are C compatible, but they have a lot more limitations, a little bit more difficult to work with, right? So there are pros and cons for each of them. So let's see how they work. I have quite a bit of code here in the slides, right? Right, and STL stands for Standard Template Library. I have quite a bit of code here in the slides, so I'm going to walk through this, and then I'm going to demonstrate some of this code in VS Code in C++, right? So let's get started here. These are the fixed size arrays, right, that are C style. These are the standard library arrays that have a little bit more functionality. How do we declare an array? This is our first step, right, when we want to declare an array. If we're working with static size arrays, this is very similar to C, right? You require to have homogeneous elements. The size is fixed. So you do something like int numbers 5. That means I'm creating an array of 5 elements, and here I'm initializing the elements. If I do something like int numbers 5, and I use just the curly brackets, this is creating an array of 5 elements, right? So it's saving 5 slots in memory, but everything is initialized to 0 in this case. So this is how we initialize static arrays, C-type arrays. You'll notice that declaring arrays with the standard library is a little bit different. First, we have to include the array library here, right? So we import a library. And then this is how we declare them. I'm saying I want an array of type integer of size 5, and here's the elements that I will have in it. I'll have an array of type integer of size 5 that is going to be empty, which will initialize all the elements to 0. So the syntax looks a little bit different whether we're using a C-style array, which is static and fixed size, or a standard array. Let's see how I access and update elements. This is pretty similar to both of them, right? This is the traditional way that we access elements in an array. This is the name of the array. We use the square brackets, and inside the square brackets, I put the index that I'm trying to access. So right now, I'm trying to access element at index 0. Right? Same here, I'm trying to access an element at index 0, or I'm trying to modify the element at index 2. I will note something very quick. These brackets that we see here are declaring the size of the array, right? Size 5. These brackets over here, combined with the name that we gave to the variable array, tell us access this element. Access this element so we can print it, access this element so we can modify it and set the value 10 into it. Access this value so that we can print it, access this value so we modify it and we can put the value 10 in it. Okay, so both of them are very similar in terms of how we access and update elements. Something to be very careful about is with C-style arrays, if we're trying to access an index outside of the size, namely, if my size is 5 and I'm trying to access index 99, this will lead to undefined behavior. There's not going to be an error during compilation, right? But you are trying to access a slot that is not part of your array, so the behavior could be undefined. You could get a value, you could get something that was stored there from a previous operation. This is the downside of being able to access memory directly with these kinds of arrays, right? The upside is that you have a lot of power over the memory. The downside is that there's no safety checks in place for you. You have to do that yourself, right? So you have to be very careful to make sure you're not going over the array indexing boundaries. On the other hand, with standard array library, right, there is bound checking. You can use the operation .add, right? That either is going to give you the value at the specific index or throw an exception if you are out of bounds. Okay, so this is a much safer operation that allows for you to be able to check if you're out of bounds, right? So in a nutshell, while accessing and updating looks the same, right? With C-styles arrays, be careful you don't have safety nets in place if you try to get out of bounds. With standard arrays, you do have safety nets in place by using the add operator, which will throw an exception if you're out of bounds. If we're trying to get the size operator of static arrays, we need to do a little bit of math, right? The size doesn't come with the array, doesn't get stored by the array. So when I'm creating an array of size 5, there's nowhere that I'm storing that value of 5. So in order for me to figure out that particular value 5, I have to do some memory addressing. I have to figure out how many numbers I have stored in my array. And I have to divide that by the size of the first number that I'm at, the indexing where I'm at the first point, right? So I'm trying to figure out basically what my current size in memory is divided by the size of the first element, right? So I find that very quirky because in other programming languages, there's none of this, right? You don't have power, as we're going to see in Python as well, you don't have power of the memory. So internally, you're keeping track of size, right? But here we're not. So in order for you to know the size, you have to do this mathematical operation. There's no built-in size function. On the other hand, the standard array library has a built-in size function. This function internally is doing something like this, right? But it is being handled for us. We don't have to manually calculate the size. It comes with the language. So hopefully this first comparison of operations declaring, access, and updating and size between C-style arrays and standard arrays gives you a little bit of that insight into how one tends to be more safe in terms of how memory is being accessed and used and has a lot of safety nets and allows a lot of functionality versus the other one, you have to implement those safety nets. You have to be careful yourself what operations you're doing, but it gives you a lot of power with the underlying memory. Let's look at a couple of more operations, provided that we are here, right? If we are trying to iterate through the C-style array, this is an example of iteration, right? We need to keep track of the size again, because we don't know what the size is. We don't want to go out of bounds, and we access the elements as usual. Here, we have access to the size via the size function. I can use array I can use array.add. Either operation is fine. So this first method is using for loops to iterate over arrays with a given index, right? I will note something here. We have this operation called size t, right? We could easily substitute this with an integer. Basically, it's making sure that we are not going over the amount of elements that an int type can actually store, right? We're not going over that. But for the purposes of this exercise, you can usually use int here because we have arrays of small size. So this was method 1, using indexing and for loops. Method 2, you can use a range-based for loops, right? This is the operation that was allowed after C++ 11. So if you're trying to compile with a compiler before that, you're not going to be able to have this functionality, but after 11, it's pretty standard. This is a range-based function, so you're not iterating over indices, you're iterating over values, you're iterating over values, right? So this looks similar in both of them. And finally, the third way is obviously using pointers. We are working in pointer-based languages with C++. So you could start at the beginning of your array. That's a pointer. You could iterate until you hit 5 elements after, and again, you have to keep the size here yourself. You increment the pointer, just like we do with pointer arithmetics, and then you are printing what that pointer is containing. Similar thing on the other side, right? But instead of starting at the numbers, we're using the function data that allows us to begin at the very beginning of the array, and then we continue until we reach the end of the array, right? We increment the pointer and print that pointer. In this case, the array itself is working as a pointer. I'd encourage you to review the lecture from the Intro to C on pointers and pointer arithmetic to better understand how these operations and iterations are working as we're jumping element by element, right, via the pointer incrementation in both of those scenarios. In terms of removal for C-sized arrays, there's no functionality for that. If you want it, you'd have to implement it yourself, right? So basically, you have to remove an element, shift the elements. There's no dynamic resizing. You have to reduce the size that you're keeping track of, right? So this 5 will become a 4. In terms of removing with the standard arrays, you will also have to shift the elements manually and reduce the size. There's also no dynamic resizing here. This provides you, though, a little bit more features of safety because you can access the element more safely and you can access the size more safely. But for both of them, there's no functionality that automatically removes an element. When we work with dynamic arrays, we're going to see a little bit more of that. Finally, there's a bunch more operators that come with the standard array for safe handling of your arrays. We also have iterators, which are structures that allow you to iterate through your data to improve complexity or easiness and flexibility to go over the array. We're not going to discuss iterators in this course, but I'm going to give you this slide with information on how you can learn more about it. You can use the C++ reference to get more information on any of the given methods that come with the with the fixed size standard library array. I've included a link up here as well. But these are some of the functions that we saw or methods that we saw. We have size, right? We have at. We can get the front and the back of the array easily. We can swap elements and many, many, many more, right? Those features take care on their own internally about the safety of bounds checking and making sure of keeping track of the size of the array so we don't have to do those quirky memory calculations, have iterators and return pointers at the front and the back of the array, and so on and so forth. So more in general, a lot of people would suggest you use something like this when you're doing implementations, but certainly if you needed more power and more flexibility over the memory, you can use a C-style array. So to summarize, pros and cons and properties of each of the C-style based arrays and the standard arrays, right? So do we have bound checking? Absolutely not. There's no protection with C-style arrays. You can have undefined behavior when you're accessing some memory location. With standard arrays, yes, we have the at operation that will throw an error if you're out of bounds. If you're trying to get size, you have to do it manually with a C-style array. You have to do the quirky calculation of where you are at in the address divided by the beginning of your address to get how many elements are there. But with standard array, we have size, which is manually doing that, but internally, right? We just call size and we're fine. There's no support for iterators with C arrays, but there is support with a standard array. The C array or a standard array, neither of them resizes dynamically. They're all fixed size, but this one, right, has more functionality, flexibility, and safety than this previous one. So they're both non-dynamic, they're fixed size. There's not really any functions that we use on a traditional C array, but we have a bunch of functions for the standard array that also matches standard array, standard library algorithms that we'll see in the future lectures as well. Safety is extremely low. You have to have manual checks to make sure that things aren't going out of bounds, to make sure you're not accessing locations in memory that don't belong to the array, to make sure that you're not running out of elements in the array. But with a standard array, the feature safety is very high, right? So you have more flexibility there in terms of safety. I hope this was a very good introduction to arrays. I want to show you a little bit of how this works in VS Code before we jump to looking at arrays in Python, as that's going to be quicker. So let's go very quickly to VS Code over here. Okay, and I'm going to show you how you can also use these code that I provide with the lecture slides as a way to reinforce the material. So over here, I am first showing a bunch of things that we can do with static sized arrays. I am declaring a static size array. I am declaring an empty static size array. I am accessing index 0 in the first array. I'm accessing and modifying index 3, right, in the first array. I'm getting the size of the array. There's no built-in size, so I have to do this manually. And then I'm going ahead and printing that size of the array. And then I have the three ways that we discussed for looping, right? If I go ahead and compile this code, and again, I'm going to use my Clang compiler. So if that works for you, go ahead and do that. Otherwise, you can do the play button up here, but this is a little bit more convenient for us to use in the terminal. And then I'm going to go ahead and run this code over here. In the output, I'm going to get static array, right? So I'm getting the first print value at index 0. I think we're over here is 1, right? And that's true. The value at index 0 is 1. The size of the array is 5, right? That is also correct here when I'm printing the size of the array is 1, 2, 3, 4, 5, right? I'm using a for loop and going over the elements 1, 2, 3, 10, 5. You'll say, Professor, why is this 10? Well, because we went at index 3 and changed it to 10, right? So this is index 0, index 1, index 2, index 3, right? So this is index 3. I changed this to 10. All three operations, whether I'm printing with for loops, with a range, or with a pointer, should give me the same result. So all four loops are working correctly. Let's go ahead and look at the standard array implementation. This is, as we said, a little bit different how we declare the array here, right? I have to declare the type of the array. I have to declare the size. This is how the standard array is keeping track of the size internally, right? It has a property called size, and we'll see how to implement that when we work with dynamic arrays. So I'm creating the array here, and I'm creating an empty array that gets initialized to 0. Again, I'm getting here the index at 0, which should be 1, and I'm changing the value at index 2, so it's 10. So 0, 1, 2, this should actually become 10. Similarly, I'm going to use the at operator to change the index at 0, and then I'm going to go ahead and try to change the value at 2. This actually is not going to throw an out of bounds exception, but we're going to modify to see what happens, right? So this should throw exception if out of bounds, try with the value 99. Okay, so we're going to try this in a second. Then we check the size of the array, and again, I'll go ahead and print with my for loops everything that is going on here. Okay, so let's go ahead. I am going to run this one more time, right? I will see that the value at index 0 is 1, right? So this is using the bracket notation. Value at index 0 is also 1 using the at notation, right? I went over here and changed the value to 10 so that when, whoops, apologies about that. So then when I'm printing, I'm getting 10, right? When I'm printing, I'm getting 1 to 10 for 5, 1 to 10 for 5, right? Because the index I'm changing is 2, right? So 0, 1, 2, I'm changing this value. Let's go ahead and change the index at 4, right? So this is 0, 1, 2, 3, 4. So I'm going to change that 5 to 55, okay? So we're still within bounds. I'm going to go ahead and compile one more time, and then I'm going to go ahead and run. Now I'm going to see that at 55 changed, right? Because I said 55. What if I were to try and get an out of bounds, right, with a value 99? So I'm going to go ahead and put 99 here. I'm going to save this, and I'm going to go ahead and try to compile. And then if I run this, is going to give me a termination. There's an exception of type out of range with array at, right? So it's telling me that it found a specific error in my code, and that's because of that 99, right? So let's go ahead and change that back to what we had it at 5. So I'll compile, run again, we're fine. But what if we were to do that 99 here, right? Or up here when we're trying to change the value. So let's try to do it up here. If I'm trying to do this 99, right, assign 10 to the fourth element, but now I'm trying the 99 element, we'll see, right, that this is not going to throw an index out of bounds errors. This is the part that actually does behavior that we don't necessarily know what's going to happen. In fact, let me go ahead and actually print here static value at index 99, right, is, and let's print the 99 here and see what it's going to tell us. I'm going to put some exclamation marks here so we know exactly where we are in the code. So I compile, I'm getting a warning, right, but not an error, right? I'm just getting a warning. This is VS Code being nice to me and giving me a complaint, but this is not an error, right? So if I go ahead and run this, it's going to run perfectly fine, right? And it's going to tell me that the element at index 99 is 10. And that's absolutely not true, right? Because if my array is going through the elements, I don't have an index 99. So the behavior is completely unpredictable in that case, right? Similarly, over here, if we were to go and try and do 99, and then I'm going to go ahead and copy this value over so that we can print it. And again, I'm going to put exclamation points here so we can see what's going on. When I am trying to compile, again, I may get some warnings. This is VS Code giving me warnings, but when I run it, no errors whatsoever, right? So this is completely, should be an error, right? Because I don't have an index 99, but it's not giving an error. I'm accessing somewhere a memory location, right? Changing a value there. It's not part of my array, okay? So I hope that this gives you a little bit more hands-on experience with how we work with the static arrays, both the C-style ones as well as the standard arrays in C++. I encourage you to delete this file and rebuild it from scratch so you can get comfortable with the syntax of the arrays. That's the only way we can learn. And in future lectures, we will use both a C array and a standard array as the basis of discussion for other data structure implementation. So that is all about the arrays in C++. Let's very quickly talk about arrays in Python. Unfortunately, arrays in Python are a little bit complex. There is an array module, but it's not a good one, right? It doesn't follow traditional array properties. You will rarely come across or ever use it in your day-to-day life. So we decided not to discuss the array module in Python. Instead, what is very popular in Python is what we call lists, which are dynamic arrays, and we're going to talk about in the next lecture. So don't worry about static or fixed size arrays in Python because they do not tend to be popular. But if you really needed a static size array, I would encourage you to look at the NumPy library. This is a third-party library, very popular for data optimization, data management, and so on and so forth. It gives you quite a bit of flexibility to working with arrays, especially when you have really large arrays that require much more insights and concerns about complexity and space. So if you ever need to work with static fixed size arrays in Python, I would encourage you to use NumPy and not the traditional array module. That is all, folks, for today. We introduced a new data structure, arrays. We talked about properties of arrays. We talked about complexity, both in time and space. We saw how arrays work in memory, and we saw the two implementations of arrays in C++, and the high-level implementation in Python. Thank you all for joining me today, and I'll see you next time when we will talk about dynamic arrays. Thank you.